quick comment? Thing we asked to work out for today. M dv dt equals M dv dx dx dt, right? Chain rule. Very straightforward. What good is that? Well, dx dt is just v, right? So this is M v dv dx. So in the situation that we had, we could write the equation as mv dv dx. Now I'm returning to the okay, I could write this as mv dv dx equals negative gamma v, right? And that's for, you know, the thing, the drag and the swimming pool, okay? So how does that simplify?
You can get it to where you can use separation, right?
Yeah. So, well, separation, yeah, but the v's divide out, don't they?
No, that's true.
Okay? So it gets really simple.
Right.
Well, you end up then with dv dx equal to negative gamma over m. So v equals negative gamma over m times x plus c. Okay? So velocity, now you have velocity as a function of x. Remember that one of the conditions we gave you was, you know, that x equals, you know, motion becomes imperceptible when x equals a certain value, right? Well, this tells you if you have the initial conditions and so forth, at what x your velocity would be 0. Now, in that problem, this doesn't occur in finite time, theoretically. Okay? But you do get down to the velocity, and you know, before you get very far, you have a limiting distance here. Okay? So you will get down to the velocity where you really aren't moving except with quantum fluctuations. Okay? And the probability of, well, anyhow. You know, you don't want to get into that. And the other equation would become mv dv dx equals negative gamma v squared. Okay? So that v is an exponential function of x. So in looking at the original problems, let's apply this trick. Because this changes our variable from t to x. Okay? So we could solve the problem for the function of t, we could solve the problem for a function of x. And this actually is much simpler in the problem we were given. Okay? And you can also maybe try to apply it here. Okay? So you get a velocity as a function of position rather than as a function of time. And there are questions that you can answer now with velocity as a function of position that are much more difficult to answer if your velocity is a function of time. Now, the problem we started with illustrates that nicely in terms of this trick. So you really want to think that through. And I'll phrase a problem in your homework that I'll add. Okay? Because you've already got these problems. But we want to really kind of understand that. Okay?